Okay, so let's go into more sort of practical stuff here. So let's talk about how we're going to express emissivity. We've talked about this basic idea that we can represent emissivity as a function of wavelength and direction. So let's look at the different levels there. All right, so the first thing is we said up here, let me just flip this back. We said that emissivity for lambda, theta, and phi, that was spectral directional emissivity. The second thing we can do is just look at, let's assume that we take a surface and we say that it's diffuse, right? A diffuse surface, by definition, means that the light that's leaving the surface is equally probable to leave in any direction. So by that definition, we're saying there is no such dependence on theta and phi, right? We're throwing that away. So if it's a diffuse surface, this is just epsilon sub lambda, and we call this spectral hemispherical. Oops, sorry, my handwriting today is a little subpar. Spectral hemispherical emissivity. Right? You can kind of see where the words come from, right? Spectral means that there's a dependence on the spectrum, right? On the wavelength. Hemispherical now means like instead of looking at a specific direction, you're looking at the total hemisphere around this emitting surface. All right? And then the third thing we can say is, well, we just want plain old epsilon, in which case we're saying that there's no emissivity dependence on wavelength. Okay, so we would call this total hemispherical all right, another word for, let's see, this second one up here, I'll just write it above it, but this up here is a diffuse surface. Down here, this is something called a diffuse gray surface. All right? So think about that for just a second. So diffuse surface makes sense. We have emissivity as a function of wavelength, but it's not a function of direction, so it's diffuse. Diffuse gray, where does this come from? Well, if we have an epsilon that's not equal to 1, right, it is emitting less than a black body. That means it's also absorbing less than a black body would. So if it's absorbing less and it's sort of reflecting some light, it's going to do that reflection independently of wavelength, right? We're saying that wavelength for that last one is not important. So what is the color that you see which has equal distribution of wavelengths? It's gray, right? So black to white with gray in the middle, that's no wavelength dependence. So it's an actual physically gray surface that we're talking about here, right? That's where that comes from. Just to kind of show you what this might look like if you plot it out. So here we have, let's say, wavelength here with micron in units, and then what we're plotting is emissive power epsilon or E sub lambda. So for a black body, remember the black body curve maybe looks like this. This is our black body curve. So if we had some, let's say we're taking this one over here, epsilon sub lambda. Let's say we have some epsilon sub lambda. What is my emissive power of the real surface going to look like? Let me just draw this in a different color here. So the real surface, let's say we start off with a very low wavelength. The emissivity is really low, right? So maybe it's going to look like this. Right? There's a large fraction of the emitted light that could be emitted is not because the emissivity is low. And then let's say as lambda goes up, the emissivity goes up, and so maybe your real surface actually looks something like this. Right? So over here, sorry, this is my real surface. All right, so if I was going to maybe, I didn't leave myself a lot of room, but let's say I'm going to plot emissivity, right, as a function of wavelength. that might look something like over here it's really low, and then as it goes up it maybe looks something like this, right, where this is 1 here and this is 0 here. So this is maybe like a characteristic of a real surface that you experience, and you have some function where you have to account for the transition in emissivity. Okay, I'll stop for a second. Any questions? Yeah?
On this graph, is there a way that the real surface could have a higher emissivity than a black body?
Yeah, it's a good question. So could the real surface ever have a higher emissivity than the black body? No, it can't. And the reason is the black body is sort of the theoretical maximum. Right? You can't really have a higher. The only way that you might, in a real system, you might look like a higher emissivity or emissivity greater than 1 is, let's say that you have like these energy states, and the individual atoms, like if you look at an individual atom, it might have like a higher energy state that's emitting. And so you see this kind of spike because it's sort of forced into the energy state. And actually, if you look at the solar spectrum, you see in places where it goes above the theoretical black body. We'll look at that later. But if you take like at the unit that's actually vibrating at its temperature, it can't. It's the theoretical maximum. Okay. Any other questions on that? Okay. Again, just kind of conceptual stuff there. Let's talk a little bit more about real surface characteristics. There's kind of 2 characteristics I think are important here. So one is basically the energy balance on a surface. Let's say that you have, I don't know, let's say we've got some rectangle like this. And I'm looking at radiation that's coming in. So I've got some radiation that's coming in like this. There's, in terms of an energy balance, there's kind of 3 different things that can happen. So if what I'm doing is I'm taking energy coming in, I'm trying to account for all the possibilities of what could result. What are my choices? Well, the first thing that can happen is a ray that's coming in, it can be absorbed at the surface, right? We would call the property associated with this absorptivity. Right? It's the likelihood of being absorbed. Well, the second thing that could happen would be the light comes in, it's maybe refracted, and then transmitted. So we would call this property transmissivity. The third thing that could happen is the light comes in and is reflected away, and we would call this reflectivity. Okay, so we see that these are kind of the 3 possible considerations. And we also note that these 3 things are expressed as fractions of the total. So if they're fractions of the total, I can do an energy balance that must equal 1, right? So the 3 outcomes must total 1. So I can say 1 is equal to absorptivity, let's call that alpha, right? Alpha, which is going to be a function like emissivity of lambda, theta, and phi, plus transmissivity, let's call that tau. This is different from shear stress, right? This is a same tau, different idea. Tau, lambda, theta, phi. And then let's call reflectivity rho. So rho, lambda, theta, phi. So that's equal to 1. Okay, so I have my 3 outcomes. They all have to equal 1. I want to stress the importance that the surface I'm assuming here is a general surface, is a generic surface. So I don't know anything about its emissive or absorptive properties. But what we do know is that if you pick a wavelength and you pick a specific direction, these are the 3 things that can happen. Okay, we can take this kind of universal energy balance and we can extend it to the other types of surfaces. So if I said I have a diffuse surface, right, so for a diffuse surface, now there's no angular dependence. I can then say alpha lambda plus tau lambda plus rho lambda equals 1. If it's a diffuse gray surface, then I can just say alpha plus tau plus rho equals 1. Okay. So these are kind of the three permutations, but it's situationally dependent, right? You have to, you can't use like diffuse gray if you have some functional dependence of emissivity on, or absorptivity, these other properties on wavelength or direction, right? So just be careful when you're using that. Another thing I want to point out here is this reflectivity bit here. So let's look a little bit more carefully at what can happen with reflectivity. There's reflection that can happen. So let's say we have like our ray coming in like this, and it's coming in at some, sorry, let me draw this a little bit more carefully. So let's say we have a ray coming in like this, and it's coming in relative to the normal here at some angle theta. That is, like, there's no likelihood of directionality. Then when it's reflected, it might be reflected this way, or it might be reflected this way, or this way, right? The probability of each of those is equal. In this case, right, we call this diffuse. Let's say, on the other hand, I have a ray coming in at the same angle relative to the normal, it's theta again, and this is like a mirror surface. What do we expect to happen? Well, the ray is going to be reflected at exactly the same angle that it came in, right? And we would call this a specular surface. So specular is not spectral, right? Spectral is spectrum. Specular is like having to do with the optical quality of the surface. So just keep in mind that there's these different properties. Again, this is something that you really wouldn't get into until you did like imaging optics or any kind of heat transfer where there is this functional dependence. But just want to point out that this exists and you should know what it is. And then there's like degrees of variation here. So you can have a specular surface which has some diffuse component to it. So there's like a mixture of these two things that can occur.